Hi everyone, I'm Weiting from Johns Hopkins University. Today I'm going to present our paper Multilingual Representation Distillation with Contrastive Learning. This work is also a joint work with colleagues from Meta AI. In this paper, we aim to improve the sentence representation for various languages, especially for low-resource languages. The sentence representation here is just a high-dimensional vector form that we encode our input sentence into. Let's first introduce some of the prior work used to learn a sentence representation. One of the most widely used methods is to fine-tune a Siamese structure model as shown on the right, like sentence transformer, sentence BERT. Such methods are effective for high-resource cases where we have a lot of aligned sentence A and B to fine-tune the model. Under our cases, though, we do not have existing or very few existing parallel data to align such representation, which makes the Siamese structure fine-tuning method less effective. Therefore, we resort to another method, multilingual distillation. This multilingual distillation architecture, or LaBSE as so called by its author, is shown on the right. So different from the Siamese structure fine-tuning, now we have a specific student encoder for source language and teacher encoder for target language. And here, we try to distill the information from the teacher encoder to the student. In our case, the target side is normally high resource, such as English, so we can pre-train the teacher encoder in representation on English and fix the parameters. Then we distill the information by computing the cosine similarity loss, and the gradient only back propagates through the student encoder, which is responsible for the source language. In practice, we follow the same setup as the LaBSE paper, where we use a laser encoder and pooling laser as teacher encoder, and we initialize a BERT structure with pooling laser as a student encoder. Now to combat the low resource settings, in our case, we use two strategies. The first is back translation, which is also a very commonly used method to augment data in machine translation community. And using that method, we can augment the monolingual data for the low resource source language into a parallel corpus and use that to train our encoders. As we can see from this plot here, the amount of back translation data is much larger than the amount of clean bytext we could get from public online resource. That is because the monolingual data is much easier to retrieve than clean corp parallel data for many low resource languages. Now we introduce a different method we use to combat the low resource setting, which is contrastive learning. And we integrate contrastive learning into the distillation process and name it LaBSE CO, where CO stands for contrastive learning. So the overall architecture is very similar as before, where we have source and target that are fed into student-teacher encoders respectively. Now we add additional negative samples and store them in a queue. To store them in the memory or a queue is inspired from the prior work such as MoCo, momentum contrastive learning. And we use it because our teacher encoder is a fixed encoder, it's pre-trained, and there's no update to the parameters. So we are able to afford a large number of negative samples in the queue, and this boosts the performance of contrastive learning by a lot compared to the traditional using the in-batch negative samples. And here we have K1, K2 all the way to Kn as negative samples representation. And then we compute the contrastive loss and perform the gradient update back to the student encoder. In previous slides, we described our method by integrating contrastive learning into the distillation process. The benefit of doing so is that contrastive learning will help us to leverage the self-supervision from the dataset, namely pushing the similar sentence representation closer to each other as we can see that there are more overlaps on the right figure between the source and target sentence embeddings. To get a good performance with contrastive learning, the key is to have better negative samples to update the model. And normally we would like to have hard negatives, such as example 2, which closely resemble the target sentence but still semantically different. But for most cases, we will have easy negative samples that does not help much for the training of the model. And we notice that in some cases, there are extremely hard negative samples in the dataset, which are too close to the target to be used as negative samples. Therefore, we designed the prefiltering mechanism to help us get better negative samples. The prefiltering method is visualized to the left, and we pre-compute a target similarity between the target sentence and each of the samples in the queue. And if the samples has a very high similarity score to the target, its contribution to the contrastive loss would be disabled, meaning that this sample is no longer used. For example, the first sample here is too close to the target and it's not used in the contrastive loss. And we do some ablation study shown on the right by using different filtering threshold. And we see that using a threshold of 0.9 achieves the best performance in our downstream task that we are going to explain later. But overall, the message here is that by adjusting the threshold, we can filter out the extremely hard negatives to improve the performance. But if the threshold is too small, then it would actually harm the performance by filtering out hard negatives. Now that I have introduced our method, I'm going to briefly talk about some of our experiments to validate the effectiveness of our approach. For the details of the experiments, please refer to the paper. So in this experiment similarity search, we are given a parallel corpus, which means the source and targets are aligned. And then for each of the source sentence, we compute the similarity between the source and each target sentence using the trained encoder as well as XSIM score, which is a variation of cosine similarity to compute the score between the sentences. And for each, once we compute the score for each target sentence against the source, we select the target sentence that has a highest score. And if that target sentence is not the correctly aligned target for the source sentence, we increment the error by 1, and then we compute error rate in the end. So the figure here, as we shown, error rate is lower the better. So the baseline is language agnostic BERT sentence embedding developed from Google. And this is pre-trained on hundreds of languages to be used as a good representation. It's not specifically pre-trained on those African languages we shown here, but it's pre-trained on some other languages belongs to the same language family. But it's still not performing well because this is very low resource languages. Then we have the LaBSE approach, which is a multilingual distillation process described in the previous slides. And this can significantly boost performance because it's specifically trained on those language data. And further, with back translation, we can see that it improves the error rate by a large margin, again, further showing that back translation is simple and effective approach. Based on that model, I use contrastive learning. We have 2 versions, and in this data set, in those experiments, we show that using back translation with contrastive learning could achieve the best performance in terms of error rate. And this is slightly better than integrating prefiltering mechanism for the extremely low resource African language data. Another experiment that we have done is corpus filtering, where we are giving a large and noisy corpus for different languages, and we're trying to filter out the noisy data from the corpus and use the remaining clean data to train a machine translation system that is evaluated on Flores test data, and we replot the blue score here. So one of the strong baseline system we use is WMT-based system, shown in the red color, because this corpus filtering dataset is actually a shared task from previous WMT competitions, and those WMT-based systems are the winner of the previous year systems working on this task. So they are specialized model for those languages for corpus filtering. And we are able to improve, are able to beat their performance by using LaBSE with back translation data, for example, which shows the effectiveness of augmenting with back translation data. However, back translation is very expensive, and because normally it costs like 5 times more data to train the model, and also to augment the data using a large multilingual machine translation model to generate on the monolingual source sentence is extremely expensive as well. So now we can see that LaBSE with contrastive learning could also achieve on par performance, as we show here on the orange and blue color. And note that for the contrastive learning approach, it does not use back translation data here. So it only uses original clean data, which is 1/5 of the model trained on back translation data, and it can achieve par performance. For more details, please refer to our paper, and thank you for listening to our presentation.